Hey, welcome back. Today we want to look at the divergence theorem, and the story of the divergence theorem will begin back here with the line integrals of vector fields. So originally we kind of defined the line integral of a vector field on a curve to be kind of the sum of the alignment between the direction of the curve in space. So again, maybe we have some curve verping around the XYZ space and it's submerged in a force field of some sorts. So on the curve itself, if you consider it like the path of a particle, there's going to be some tangent vector, but there's also, we can attach to it the force field vector and consider the alignment between the two as a dot product. Okay, so we had line integrals at that point, which were kind of sums of all these increments. We put it in terms, the context of work from physics. And so we had these, I guess, work increments, which would be f dot t times the change in arc length. Okay, and then we went and add those up, and we got our nice little f dot dr, the line integral of the force field on the curve. Okay, so that's kind of where we started. From there, we saw the differential form of the line integral, which gave us a different way of writing out the line integral of a force field on a curve. So just by doing some tricky manipulations here, we could rewrite dr with regards to the chain rule, dr over dt times dt, and then rewrite f as vector m comma n, and then write dr dt as x prime of t comma y prime of t dt. And then if you did take the dot product there, you would get m times the derivative of x with respect to t plus n times the derivative of y with respect to t. But if you kind of thought of distributing the dt parts would cancel, and you get m dx plus n dy. Okay, so that's kind of where we were in that section, and I think that's all we need for our part of the story here. The change then comes, the next part of the story then comes in the Green's theorem. Okay, so Green's theorem was a way of rewriting that differential form as a double integral, right? So essentially, we take this single integral here, this curve line integral, and if we want to, we can do this transformation, and it makes life easier because maybe instead of having to integrate, this is a line integral, so maybe instead of having to do some crazy integral over some weird conglomerate of lines, which was annoying because you would have to go through and parameterize, C1, C2, C3, C4. Instead of doing that, you could just integrate then over that region and get your answer, right? So that was Green's theorem. And so basically, essentially changing a line integral into a double integral over a region. So okay, so that was nice. So that's kind of part two of the story. Then the part that leads into us are these alternative forms of Green's theorem. All right, so we want to talk about surfaces in particular and not these line integrals. We want to talk about surface integrals. And for surface integrals, rather than talking about tangent vectors, it's more it makes more sense physically to talk about normal vectors. So instead of having this curve in space, now you have some sort of solid object in space. Okay, so maybe something like this. The deal is it'll be submerged in a force field, right? All over the object there are normal vectors, and we want to kind of talk about the alignment between the force field and these normal vectors, and that will represent kind of the what they'll call well, what we have called the flux, right? So at each normal vector, then you could attach force field vector and talk about the alignment between the force field and these normal vectors. You know, again, if the alignment, you know, if the force field and the normal vectors are kind of aligned, then there's going to be a lot of flux. There's going to be a lot of movement out of this membrane. Okay. The only issue then becomes because we have to have solid closed objects, the issue will become what happens when we have like these types of solid objects where there's basically, you know, 1, 2, 3, you can't see side 3, side 3, side 4, and then side 5 on the back. You'd have to do 5 surface integrals to get the flux out of that. Right, so like above here, you have to do 4 line integrals, which is annoying. Here, you have to do 4 surface integrals, which is annoying. So wouldn't it be nice if there was some way to convert a bunch of these surface integrals, like we did for going from line integrals into just doing basically an area integral? Wouldn't it be nice if there's some way to go from a surface integral the flux integral in particular over to a volume integral? So we could just do a triple integral on the object and be kind of done with it, rather than having to do 20 surface integrals, you know. And it turns out that the alternate form of Green's theorem kind of gives that to us. So originally, you know, because it's f dot t in our line integrals, we can't directly kind of use so remember, the line integrals were about the alignment between the force vector and the tangent vector. Okay. Now we want to know alignment between the force vector and the normal vector, right? So we can't kind of call upon Green's theorem directly, because that was all about this f dot t issue going over to a double integral. We want to go f dot n over to a triple integral. So, but what I'm saying is that we've kind of already seen this. It's just you've probably forgotten because the book uses it as kind of a footnote in the Green's theorem section, right? They introduce it. You don't do it in the homework, but there it is, right? It's this alternative form for Green's theorem that you're kind of seeing here at the end, where they do in fact kind of generate an alternative form for Green's theorem, but with regards to the f dot n as opposed to the original f dot t. Okay, so recall then Green's theorem, the alternative form of Green's theorem. Recall the alternative form of Green's, which says that the line integral of the vector field on this curve S can be rewritten as a double integral over this region R of the divergence of f dA. Okay. And that turns out to be kind of what we want. All right. So what we want is then a way to transfer from this surface integral, and these should both be vectors, and just rewrite it as a triple integral over volume. And it turns out that it's basically the same spiel. except instead of going from a single integral to double, you're going from double to triple, and we'll use a Q to represent a solid. Okay, and it turns out what you have here, just by kind of slapping in another integral symbol, this is the divergence theorem. And the proof of this is basically exactly the same as the proof for Green's theorem, so I'm not going to go over it. It's in the book, you can read it. So now let's go ahead and fast forward to the divergence theorem here in 15.7. And here they are reminding you of the alternative form of Green's theorem, and then they're complaining about how hard it would be to integrate a solid object where you have to do multiple integrals because the solid object is like a composite of a bunch of different quadratic surfaces. And then they introduce the divergence theorem, which solves the issue. And the proof of it, like I said, is very similar to the proof of Green's theorem, where you're kind of chopping up a differential looking form into a bunch of pieces and then equating the little pieces to the pieces of the volume integral. So I'll leave that to you, and you can go ahead and read that. But you can see here in this picture, what they're having to do is do 3 integrals for this one object. Okay, and again, it's akin to this idea where it's way easier, like with Green's theorem, to do a double integral over an area than it is to do a line integral over 4 curves. Okay, and it works. We also want to talk about physical interpretation here, but let's get this sort of the use of these out of the way. We want to do one where we kind of verify the divergence theorem. The homework that I usually assign has a lot of verification problems, but I kind of took those all out because you do one of them, you got the idea, and most students will just end up always doing the triple integrals once they learn that doing a double integral is not a lot of fun, especially if you have like 6 surfaces. So anyways, I want to do something similar to example 2. I don't want to do example 2. Oh, my problem's exactly the same as example 2, so this is not going to be painful at all. Yeah, so here. So that was me introducing the divergence theorem. So this is section 1. Kind of my impromptu introduction. Thank you for bearing with me. And then section 2, we have verifying, which just means we're going to do the integral both ways. You'll see the one way is annoying and you'll never want to do it again. And but they both work, right? They'll both give you the same answer. So mine is like example 2. It might be exactly the same as example. No, it's not. That's a sad thing. Okay, so you'll always be given a force field of some sort in space. And then we'll be given some sort of closed surface. Okay, so we have here the surface bounded by the graphs of z equals 1 minus x squared minus y squared, which is a elliptic parabola, and then z equals 0, which is the xy plane. Okay, so if you need a picture, you could do a cross-sectional analysis. You know, let z equal 1 minus x squared is an upside-down parabola, shifted up 1. Z equals 1 minus y squared is the same thing. And then x squared plus y squared is equal to 1 when z is equal to 0. So you get a circle there in the xy plane. So ultimately, the picture is going to kind of be this kind of thing. Ugh, it's not a very good picture, but hopefully it gets my point across. I don't know. Okay, maybe it's more like this. look better? I don't know. All right, so it's that sort of thing. There's two kind of surfaces here. There's the z equals 1 minus x squared minus y squared, and then there's the plane the xy plane, which is z equals 0. So we need to do the surface integral of the force field on both of those surfaces. And so we'll make surface 1, I guess, the z equals 1 minus x squared minus y squared, and then surface 2 will be the bottom, z equals 0. So for both of those integrals, you need your dot product between the force field and the normal vector. Okay. The unit normal vector, but remember the denominator of the unit normal vector will cancel into this ds element, and so you'll just basically have the force field times dotted with the normal vector. So anyways, the first normal vector, we need a gradient of g, so I need to rewrite s1 as a triple variable function xyz. So in this case we want z, we want the outward or upward unit normal, and we'll have z plus x squared plus y squared minus 1 is 0. So the gradient, which will become our normal vector, will be 2x comma 2y comma 1, and so we'll have the double integral of where's our force field? I lost the force field way up there. xz zy 2z. Okay, so that thing xz zy 2z dotted with our sort of normal. So this would be 2x, 2y, and 1. And then we could go dA. Usually you're going to want to end up going to polar coordinates with these guys, and a lot of times it doesn't look like it. So I mean, even me, when I first started, I would do both integrals until one got stuck, and then I would just switch over to the other one. I mean, sometimes both of them are just too, they both kind of suck. There's no other good way to say it. Right. Anyways, right now what we have to deal with, what do we have? 2x squared z and plus 2zy squared, and then plus 2z. Okay. dA. So I'm going to go to the polar coordinates. The area that we're integrating over in polar coordinates then is going to be r equals 1 for the circle, and then we're going to be going on theta from 0 to 2 pi. Okay, so my double integral then will become 0 to 1, 0 to 2 pi. I'll have 2, and I'm going to end up having to probably, so how do I want to do this? I think it'd be easier here to factor out the 2z. So you see you have 2z times, what would this be if I factor out the 2z? 2z times x squared plus y squared plus 1, right? So you'd have 2z times r squared plus 1, and then you have the r d theta, right? So seems like I'm missing something though. X squared plus y squared it's a 2z squared, isn't it? That's the issue. Going back up here. It's 2z times, no, this is 1. But but it's 2z. It's a typo, sorry. So originally the vector field, I miscopied it. It's 2z squared. Wonderful, sorry. So this would be 2z squared. So this is 2z squared. Very sorry. So I guess I have a plus z in there. Plus z. And then just make sure I'm right with my notes before we progress. Let's see, and then you have r d theta. I mean, that's got to be right. It's 2x squared z, 2zy squared plus 2z squared. I factored out the 2z, so I would have x squared plus y squared, which is r squared, plus, it should be r squared plus z, not r squared plus 1 plus z, it's just r squared plus z. I hate to think I made a mistake in my notes. So r squared plus z like this. Okay, so what do we have then? Might as well back distribute it. I don't see any reason why not. It's just such a mess. 2z r squared plus, and it's going to be r cubed when you distribute that r. And then 2z squared r dr d theta. And then it's going to be integrating. Oh, we have to get rid of the z. That's the problem. Okay, so z is equal to this. 1 minus x squared. See what I mean? It's like, I don't know, I don't want to. Alright, so, yeah, let's keep that z on the outside for right now. So it's 2 times 1 minus x squared. Z is 1 minus r squared, right? So it's 1 minus r squared. So I'm going from here. And then we have r squared plus 1 minus r squared times r dr d theta. So never mind this business. And then we have 2 times, because the r squares cancel, you just have a 1, and then you could distribute this r. So we'll have 2r minus 2r cubed dr d theta, and I think I'm on the right track right now. Okay, so let me go ahead and integrate firstly with respect to r. So I have 2r squared over 2, which is r squared, minus 2r to the 4th over 4, which is r to the 4th over 2. And then I have to evaluate that from 0 to 1, d theta. So that's going to be, what, 1 minus 1/2, which is 1/2, which I could factor out. The integral of 1 d theta, basically. So that would be 1/2 theta from 0 to 2 pi. And then 1/2 times 2 pi is just pi minus 0, so pi. That's the first integral, okay? Then for the second integral, again, it's this z equals 0, right? So this integral is going to be a lot easier. This is the one case where you actually have to use a downward unit normal vector, okay? Because you want those normal vectors to be pointing to the outside of the object. So on the bottom surface, you want the downward pointing unit normal vector. Thankfully, this surface is so simple that that normal vector, you can even get the unit normal vector, is just going to be 0, 0, pointing straight down in the z direction, -1, right? Okay, so the force vector then for this, okay, so we need the force vector dotted with this normal vector, right? So I put the second integral, so this we say is S1, and then we'll put S2 up here. Okay. Okay, so we'll have our force field again, x z comma z y comma 2z squared dotted with 0, 0, -1. And it becomes easy because z is 0, right? So the force field vector is just 0, 0, 0, and then dotted with 0, 0, -1, dA, and then that will just be the double integral of 0 dA, which is going to be equal to 0. Okay. So to get your overall answer, you're just taking those two integrals and adding them together. One is 0, the other is pi. So the flux in this case, the double integral of f dot n ds is going to be pi. Okay, but now we have this other theorem, this divergence theorem, which is saying we could basically just do a triple integral over that over this object. Okay, so instead we are going to do a triple integral of the divergence of f. So the divergence of f, if you remember, you basically just take the partial derivatives. It's basically just sum the, I guess, the components of the you take the derivative of each of the components. So you need the derivative with respect to x of that guy, and then plus the derivative with respect to y of this guy, and then plus the derivative with respect to z of this guy. So the divergence of f would become then z plus z plus 4z. Okay, and then dv. So our triple integral would be of 4, 5, 6z dv, and then you have a triple integral on your hands, and you may want to convert this to polar. It's probably not a bad idea, but yeah, it's up to you. So you're going from z equals 0 to z equals 1 minus x squared minus y squared. But if you go polar, that's going to be 1 minus r squared. And then on the xy plane, you're doing the circle, so that's r equals 1, 0 to 1, and then 0 to 2 pi. And then you just have 6r z, and then you're going dz dr d theta. Okay. All right. So double integral it then, and you have 6r times z squared over 2. So there's a 2 there. And then evaluating on those limits, z is 1 minus r squared, z squared, then square it. And then you have dr d theta. Probably FOIL that thing out so I can easily get the job done there. So this would be the double integral of, we could factor out 3, right? So then you'd have r times 1 minus 2r squared, r to the 4th rather, no, r squared, and then plus r to the 4th, dr d theta. So that would be the double integral of r minus 2r cubed plus r to the 5th dr d theta, and then you want to integrate with respect to r, so you get r squared over 2. Don't forget there's a 3 sitting in front. Minus 2r to the 4th over 4, so that would be r to the 4th over 2 plus r to the 6th over 6, evaluated from 0 to 1. When you do that, the first two terms cancel. So you just have 1/6, and you could factor the 1/6 out, and you have 3/6, which is 1/2. And then you're left with an integral of d theta. And then I'll have 1/2 theta evaluated from 0 to 2 pi. So of course you get pi, verifying the theorem, right? So either way you slice it, you get a pi. To be honest, there have been times where they've given me one of these integrals and said to do it using the triple integral, and I thought, you know what, I'm just going to do the surface integrals. I end up, I mean, sometimes the time it takes you to think through which one is better, you could have just picked one and been done with it and got your work out of the way. You know, it's a battle. It's like which one is going to be quicker, how long it's going to take me to figure out which one is quicker, and then ultimately, would it have been just easier to just do what I know? You know, so I don't know. But every one of the exercises, you just do the triple integrals, and it's a little easier in my opinion. Okay, so let's go ahead and try one of the exercises. And like I said, they always kind of turn into usually polar integrals, but sometimes I'm just kind of like, I'll do the regular integral and deal with it, you know. So for example, I guess number 3, we'll do number 3. Here we have the force field given as x squared minus 2xy, and then xy z squared. And same for polar and rectangular. You'll be sitting there, which one's going to be easier, you know? And sometimes by the time you figure out which one's easier, you could have just went ahead and did the hard version. So I'm almost to the point where just do it, you know, just get your hands in there and do it, and don't sit around, you know, get a cup of coffee and I'm going to think about this. No, just do it. Get it over with. So anyways, we're doing these now with the divergence theorem. So we got a triple integral of the divergence of f. So again, to get the divergence of f, you're basically just doing partials and adding them all up. So the divergence of f would be 2x minus 2x plus 2xyz. So the 2x's cancel, and so we have our triple integral of 2xyz dv, and the region we're looking at is the upper hemisphere of a sphere. So we have basically kind of this picture. The cat is freaking out as usual, so let me get him, even though I have to pull him through a labyrinth of chords. Oh, I need this on your lap, even though this is really... Okay, so the cat must have hit my... right now I'm doing voiceover for this. Don't know what happened. The cat hit the button or something, and anyways, here I am. So we're doing the divergence theorem, so changing surface integrals into triple integrals, so you only have to do one integral as opposed to maybe doing, in this case you'd probably have to do 2, right, because you have 2 surfaces. Anyways, waiting for something to happen. Oh, here we go. Is it doing something? Yeah. Okay. Yeah, so right now I'm thinking of doing just keeping it in rectangular coordinates. So surface to surface, surface z equals 0 to z equals square root a squared minus x squared minus y squared. Then you'll see in that on the object I'm actually showing you surface to surface. Okay. So you need the volume of that object, and I believe I'm probably going to go in the polar coordinates. I need to see what I'm integrating over top of, so that's what I'm drawing next here on the right. So I'm integrating over a circle. You just consider the projection, let z equal 0, you get a circle with radius a. Right. Okay, so there's that. I'm going to try it in rectangular, I guess. Something tells me I'm going to convert the polar, but we'll see where I'm going with this. So it's going to be, z squared over 2, and then doing your substitution, it'll be the square root of a squared minus x squared minus y squared squared. So you're just going to get a squared minus x squared minus y squared. Okay, it's just that thing squared minus that thing, but that'll be 0. So you need not worry about that. The 2 goes away because it's z squared over 2. Yeah, you just get a squared minus x squared. I just put a for some reason. It should be a squared. dy dx. So I'm going to distribute. Of course, I messed up the a squared part. Then I'm going to integrate with respect to y. Probably the answer is 0 or something, so it didn't even matter, but there is a mistake, which is carrying on through the problem. And here I got to be annoyed by these square roots. I cannot believe I did not go to the polar coordinates. I probably do. I probably end up saying, oh, forget this, I'm going to go to the polar. Nope, I didn't do it. Oh, it's because, yeah, everything's going to cancel because it's symmetric. Like those y squared things, if you plug in that square root of a squared minus x squared or the negative of that, it's going to be the same thing when you square it. You'll get rid of the negative. So ultimately, you're going to have the same thing subtracted, and that'll be 0. Regardless of the mistake I made, it's just going to end up being 0. I think the moral of this story was that it doesn't. You don't always have to go the polar coordinates. Sometimes I've done problems where I went the polar and it just snowballed. It just made it worse. So in this case, it works out really nice with the cancellation and all. Apparently, I'm putting it all, writing it out in all of its glory. I don't know what I was doing there. Not sure what that's all about. Yeah. Oh, probably because I was freaking out right there because of the square roots and everything, thinking that was terrible. And now I'm noting, well, it's just turning into a big 0. That's the blue thing. Is apparently the face I make when I'm freaking out over an integral. Trying to make it look cool or something. I don't know. Okay. Next problem. I don't know what I'm doing. What am I doing? Next problem. Next problem, please. Thank you. Section 4. What are we doing now? Oh, reminding us of the divergence formula, I guess. It seems like I must have already covered that. If I didn't, well, there it is. Oh, this is where I'm going to start getting into this must be the more explaining what divergence is physically. So I kind of go back to 15 previous sections. Yeah, this is the physical interpretation. Okay. So how come you could do this triple integral instead of the double integral? And the deal is you kind of consider the object that you're working with as either a surface kind of stuff going out of it, or you could chop this region up into a bunch of little cubes and then consider the flux in and out of the cubes, right? You'd have first seen this sort of issue in the section on Green's theorem, where we had an alternative form for Green's theorem, and we had this conversion formula from the line integral of the basically the vector field dotted with the normal vector of the, I guess that would have been the curve. I don't even remember at this point, but the divergence of, and then on the right we have, okay. So you're going to get two kind of pictures here. Stuff going, you could kind of figure out the integral by just going around the boundary, or you can figure out the integral by going into each individual block and seeing what's going in and out of the individual blocks. Okay. So the first integral is related to just going around the boundary and looking at the normal vectors and adding them up. And then the other version, we're going to go around each individual block. Okay. And the deal is that individually you'll have different numbers as you kind of go around and add things up. So here, this box has two normal vectors going out. So I'll say there's 2 plus 2 going out. This next box here to the right has 1, 2 going out. As you go around the box, you can count the ones going out. This one also apparently has plus, well, this is plus 3. We've not seen a vector going in. Oh, there's one going in, so that's a minus 1. So 1 minus 1 is 0, plus 1 is plus 1. Okay, for that overall box. Okay, so that would be kind of like doing the double integral version, and then you have to add all that junk up. Okay, but the deal is when you smush it all together, like in the second box, is basically this picture I'm drawing on right now is basically the picture on the right, but with all the box smushed together. So what's happening is, like in that second box, stuff is going out of that box, but then you'll count it as going into the box right next to it. So there's this weird cancellation going on. Okay. Then this third box, it's going out on the left and then the bottom, but then it's going to push into the box above it. So there should be an arrow going into the box above it, which I missed apparently. I'll have to go back and get that one once I figure out what I did wrong. But the idea is when you smush all the boxes together, the arrows that were going out of the boxes will now be going into a box next to it. And the arrows that were going in, well, I guess they're still going in. But they will be kind of attached to the other box right next to it as an arrow that's going out. I still got to fix that one little mistake. I'm missing an arrow. You're missing an arrow. Okay, so anyways, the double integral version, to figure that out, you have to go through and add up each individual. Oh, am I doing it now? Okay, so for that first box, if you look at the total sum, and there I finally got the arrow that was missing. You just go around the edge of that inner box here, right? So if you look at the arrows, the 2 are canceling out, then you got 1 going in, 1 going out, for a total of 0, right? One thing that's annoying is you can't see where my cursor is. Like usually when I'm making my video, I assume you can see where my cursor is, but apparently you can't. So I need to fix that. Anyways, the second box, we have something going out, something going in, and then something going out. So I get a +1 overall. The third box on the bottom left, I have one going in, one going out, one going out, and then one going into the other box, which I missed. I need to put that in blue. So it should be +2 overall. Yeah. And then the final box, you got one going out, one going in, one going out. So overall, that's a +1. Okay, and then we kind of add up the integrals accordingly. So the double integral is like you're going through each box and adding up the accumulation. Okay, so 0 + 2 + 1 + 1 is for overall 4. The single integral, the line integral there, basically says you could accomplish the same feat by just adding up the arrows on the boundaries. Okay, so you'd have 1 + 1 + -1, so 1 + 1 there in yellow, and then plus a -1 going in, and then a +1 going out, and then a +1 going out, and then a +1 going out. So 1, 2, 3, 4, 5 minus the 1 going in is 4. You get the same answer either way. Okay, long story short. Hopefully that wasn't too confusing. It's kind of confusing, but the idea is that the boxes on the inside, if there's any like flux in and out of the boxes on the inside, they all get canceled out in this process. And so the double integral is the same as the integral around the edge. Long story short. Okay, and this is the sort of the other version. Like the divergence theorem we're dealing with now is taking a surface integral and turning it into an integral of like a volume integral with divergence attached to it, right? So a little bit different, but the same idea. It's just now when you're dealing with a solid object, you're, instead of cutting it up into little boxes, you're cutting up into little cubes. Okay, and it's the same effect happens. Like the cubes that are next to each other, if one's going out of one cube, it's going into the other cube. So as you would go around individually and add up all of the cubes in and outs, there's going to be cancellation. So you need not bother. All you need to do is integrate around the boundary, okay, or integrate over the integrate the surface. Okay. Okay. So anyways, from here we kind of move on to the idea. I believe that we're going to move on to the divergence at a point. Okay. So what we're doing is taking a solid object and cutting it up into a bunch of little spheres, and then we'll consider just one sphere inside of that object and give it a name. I think we're going to call it S sub alpha. Okay. And my computer just died for no freaking reason whatsoever. Okay, so S sub alpha. Okay, radius alpha. And what we want to know is what is the divergence at a point? What does that really mean? Okay. So we know the flux of F across a surface, and in particular we're going to go the surface of this little sphere is equal to the triple integral of the divergence throughout the integrating throughout the surface, right? Or throughout this object. If you make your sphere small enough, that divergence is going to be a constant. All right. We've made some assumptions about the vector field, that it's continuous. Okay, so in a small enough region, we could suppose that divergence of F is constant, and we could factor out of the triple integral. Then that triple integral is basically just the volume of that little sphere with radius alpha. So you get the divergence of f equaling this, whatever the volume is, so 4/3 pi r cubed, in this case 4/3 pi alpha cubed. Okay, we'll just call that delta v sub alpha. So the flux of f crossed the surface of this little sphere is going to be the divergence at that point times the volume of the little sphere. And of course, we take the volume of the little sphere as alpha goes to 0 and solve for divergence. We have flux divided by basically the volume of the sphere. Okay. So you kind of get a limit definition for the divergence ultimately, but so there's our flux formula divided by. So what you're thinking is the divergence is kind of a measure of stuff flowing into or flowing out of a point, and they'll have sources or sinks. So a source is where everything's going out of the point. A sink is when everything's going into the point. So that's what I'm saying. To define the divergence, then you just let the radius of the sphere go to 0. And that gives you the physical interpretation of divergence. Okie dokie. Okay. So there's that. And now I'm drawing pictures. This one's a sink. Everything's going into the point. And then you have sources where everything's going out. Great. Okay. Okay. Then I guess I'm going back to look at the book. I don't know why I'm looking at that, but there it is. Well, there's some nice groovy pictures, better than what I can do. It's incompressible if the divergence is 0. Okay, so that's the physical interpretation of divergence. So you go to the Khan Academy, they got some great videos on it. Of course, they could do them. The videos on divergence theorem are just incredible. They have teams of mathematicians working all day long. I can't even come close. But there it is. Okay. Am I going to do anything else? Am I done? I do some more exercises. I don't know if I did the video quiz yet. Number 5. I'm going to do number 5. Okay, so use the divergence theorem to figure out the flux. Okay. And of course, you're always hoping that it's going to work out really nicely. Here, the divergence is just 3. So you can factor that as a constant out of the integral, and you're home free. Right? It's just going to be 3 times the volume of that object we're integrating about. So yeah, it's triple integral is just the volume of that sphere, which is 4/3 pi r cubed. So sometimes you get lucky this way. You don't have to actually evaluate the integral. 4/3 pi r cubed. So what else? Number 8. I'm going to do number 8. What are you doing, Dave? Make up your mind. Oh, well, here's the video quiz. Very good. Number 8. All right. I think maybe this is one where I have to go to spherical coordinates. It's like, at this point in the book, I've forgotten that we even use spherical coordinates anymore. But, maybe that's what I'm going to do. We'll see. So using the divergence theorem to evaluate this, maybe it would have been easier just to do the surface integral in this case, right? Because it's just one surface. It's not like I'm having to integrate over 10 surfaces, so I really need to use the divergence theorem. But I don't know. We'll see what I do once I get started here. Seems like I'm taking forever. I must have had a long soliloquy going on. It has to be that spherical thing I'm talking about. I couldn't figure out how to do this problem when I first went and did it. Then I finally realized you have to go spherical coordinates. I promise not to put any spherical coordinates on the test. Typically those formulas are a little more awkward. Okay, so anyways, getting the divergence out of the way. Just taking the partials, adding them up. Y plus 5 plus x. Surface, I believe, is a sphere, radius 5. Yeah. Oh yeah, and so I'm going to definitely going to go to the spherical coordinate systems. When you're dealing with spheres, it's easier to use spherical coordinates. It's just the way of the world. Here I am kind of reminding you how they work. So the phi value is a rotation from the z-axis going downwards. Okay. So for instance, in this example, I'm going to have to go all the way from 0 to pi over 2. Theta is the rotation in the xy plane. It's basically just what you get in polar coordinates. It's the same theta. And then rho is how far out you got to go on that arm that's being rotated down from the z-axis. Okay, so that would be 5 in this case. Anyways, I need to put everything in terms of rho, phis, and thetas. Rho, the arm, is going from 0 to 5. It's kind of like the r value, except the arm is coming down from the z-axis. And then I need to go all the way from 0 to pi over 2 for the entire sphere. And then 0 to 2 pi for theta, all full circle. Okay. And I'm going to replace y and x with their corresponding. So it worked kind of like polar, kind of. So it'd be something like rho sine phi cosine theta for x, and then rho sine phi sine theta for y. And then instead of going r d theta, you have a different sort of factor that you have to plug in. So I forget what it is, but I'll remind myself it's rho squared sine phi instead of r. Then d rho, d phi, d theta. And now I want to integrate this thing. So what do I got? Rho cubed sine squared phi sine theta plus rho cubed sine squared phi cosine theta. So you should be able to do some simplification, maybe. I don't think that I will, though. I think I end up doing u subs or something. Well, we'll see. D rho, d phi, d theta. Okay. So with respect to rho, you're going to get rho to the 4th over 4, and then a rho cubed over 3 on that last term. Someday I'll do this. So here we go. Triple integral. It should just be a double integral now. If I integrated, yeah. So it should be a double integral. I got to erase that extra integral symbol. And I went ahead and plugged the 5 in, and then minus 0. So 5 to the 4th over 4, sine squared sine theta. 5 to the 4th over 4, sine squared phi cosine theta. And then 5 rho, so it would have been 5 rho cubed over 3. Plugging in 5 for rho, you get 5 times 5 cubed, which is 5 to the 4th over 3 sine phi. And of course I've already integrated, so I need to get rid of that. There I go. I got rid of the integral symbol down the 2 integrals. Then I need to do the integral with respect to phi. And what I think I do is I just kind of extract that and then do that integral and then put it all back together. So for this you need to do, turn it into 1 minus cosine 2 theta over 2, or in this case 1 minus cosine 2 phi over 2. Okay, and then evaluate that integral from 0 to pi, and then we should be able to piece it back together inside of the integral. 0 to pi. So plugging in pi, it'll be pi over 2 minus 0. And then plugging in 0, it'll just be 0 minus 0. So it's just pi over 2 for those first 2 terms in the double integral. Okay. Then that third part, the sine phi integral, I want to evaluate that as well. Integral sine phi, of course, negative cosine phi. Evaluate from 0 to pi. Plugging in pi, get negative 1. So negative 1 minus, plug in 0, you get 1. When all is said and done, then you get negative 1 plus 1, which just seems wrong. Having trouble with my signs here. It'll be negative 1 minus 1, which is negative 2. There's a negative in front of it, so it'll just be a 2. So we're getting the single integral now. So I keep refusing to get rid of the extra integral symbol. Let's get rid of that extra in it. Okay, Dave, whatever. So 5 to the 4th over 4. Well, it'll be over 8 now because it's times pi over 2. And then we have the cosine theta, sine theta left over. We have to still integrate that junk. And then plus 5 to the 4th times 2 over 3. And then this is all with respect to theta now. And I need to get rid of one of the integral symbols. There we go. Get rid of that. Okay. Now I just have to integrate sine theta, cosine theta, and then a constant, and evaluate from 0 to 2 pi. Okay, so integral of sine is negative cosine. Integral of cosine is sine. And then we have 5 to the 4th times 2 over 3 times theta. And evaluate from 0 to 2 pi. So we get 5 to the 4th over 8 pi. Cosine of 2 pi is 1, so I get negative 1. Plus sine of 2 pi is 0. Minus cosine of 0 is 1. There's a negative in front, so negative 1. Plus sine of 0 is 0. And then all of this junk will just be 0. And then I get 2 times 5 to the 4th over 3 times 2 pi minus 0. And so I just get the 4 times 5 to the 4th over 3 pi for my final answer. And then I probably have to go and check that with WebAssign to make sure I didn't make any crazy mistakes, which I didn't. I was probably amazed that I got it right. So I've been making lots of mistakes lately, and I just can't find my mistakes. It's one of those things. And it's just been, this whole semester has been like that. So I'll have one little mistake. I can't find it. I just don't know. Don't know what's wrong with me. I can't correct it. I can't stop doing it. Stop doing it, Dave. Okay, thank you for watching, and I guess we'll see you next time. Okay. Okay, I guess that's it. Is that it? What am I doing? I must have had something profound to say. All right, scrolling through. Oh, why you did math today? Okay. Thank you for watching, and I'll see you next time. Thank you for watching.